In section 1.2, we're going to dive into the limit definition and how it works and what it's actually telling us. So last section, we saw that we had this function f of x equals x squared plus 2x minus 1, and we calculated the limit as x gets closer to 2. What we said there was kind of an imprecise idea of limits. We said basically that means what does the output f of x get closer to as the input x gets closer to the number 2? And we found that to be 7 in this case, but that's irrelevant. We were saying f of x, our output, is getting closer and closer to 7 as the inputs get closer and closer to 2. Now, there's a problem with that terminology. Getting closer or getting near something is not a very precise linguistic language, especially when we're talking about a subject as precision-oriented as math. Does getting close mean it's within 1 unit? Does getting close mean we're within 1/10 of a unit, 100th of a unit? What does get near actually mean? So we're going to replace the language we used earlier with if x is within a certain tolerance level of 2, then the corresponding value f of x is within a certain tolerance level of L. In other words, if x is within a certain distance of 2, then the corresponding value f of x is going to be within a certain distance of L. Now, these tolerance levels are not the exact same. Tolerance level of being close to 2 is not the same tolerance level of being close to L. And that's what really we're going to see in this chapter. Now, those tolerance levels, because they are not going to be the same, we're going to replace those with a numerical value or a variable. And the variable that is historically used for the tolerance level within x, or excuse me, for x, for the inputs, is called delta. And the variable we use for the tolerance level within our outputs is called epsilon. So it's going to read like this. If x is within delta units of 2, then the corresponding value f of x is within epsilon units of L. Now, again, this is probably going to be pretty confusing right now, and that is to be expected. We'll drill down and get more in detail as time goes on. So here's the actual definition for the limit of f of x as x approaches c. So first off, we have to assume that we're looking at a number which we call c for constant. And that c for constant is going to be contained in a nice open interval so that f, our function, is defined on that open interval, except maybe not defined at c. So we want it to be defined around c. So if we have that, then the limit of f of x as x approaches c is L, denoted by this. So this means that given any epsilon greater than 0, there exists a delta greater than 0, such that for all x and I, where x is not equal to c. If x minus c, an absolute value, is less than delta, then f of x minus L is less than epsilon. Now that's a mouthful. That's a really, really complicated looking definition for limit. But mathematics is a subject that requires a lot of precision. So sometimes being precise causes us to be fairly messy. Basically, what this is saying is it's saying that if you give me an epsilon, I can find a delta so that every x within a tolerance of delta of the number c forces my outputs all to be within a tolerance of epsilon from my limit L. So if you give me any tolerance on my outputs, I can find a tolerance for my inputs, which is bounded by delta. And that's kind of how we go about doing it. We're going to use some epsilons, some deltas, and we're going to come up with the delta if I give you an epsilon. So we're going to do that in the next videos.